So let's do one more example. So what will be the strongest post condition for x is greater than 0, right? So the loop has remained the same, but the input set of program states, right, have now changed to x is greater than 0. Okay. So instead of calculating this, right, using the technique that we have seen, let's try to reason about this intuitively, right? So if I start in a program state where the value of x is greater than 0, and if I execute this particular while loop, okay, what is going to happen, right? So what happens if I start on a state where the value of x is greater than or equal to 10? So x is greater than 0, right? It also includes all those states where the value of x is greater than or equal to 10. But if I start the loop in such a state, then this loop will not even execute, right, because it won't satisfy the loop conditional. So I'll just exit out of this loop, right? So all these states where the value of x is greater than or equal to 10, they are just going to filter through, right? So this is what is probably f0, right, which are all the states that are obtained at the exit, right, before executing any iteration of the loop, right? So before executing any iteration of the loop, all these states are going to kind of filter out, right, because they will not execute, right? Now what happens to those states where the value of x is greater than 0 and the value of x is less than 10? Okay. So for this program states, if you execute the loop, what is it going to do, right? So it's simply going to so here you will actually enter the loop body, right, and then you will simply count up to 10 and then leave. Okay. So all these states, right, will result. So of course, I mean the value of x, right, it can be some real number, right? So it need not always end at 10, right, but it will exit out of the loop in a value which will be greater than or equal to 10, right? So you will get again a value which is greater than or equal to 10. So therefore the final answer is x is greater than or equal to 10. So in fact you will exit out of this loop only when the value of x will be greater than or equal to 10. So we have reasoned about this intuitively, right, but again you can apply the procedure, right, that we discussed, right, and then calculate all of those f0, f1 up to so on, right, and then get this particular formula. So we'll do one last example. So what will be the strongest post condition for x is greater than 0, but now my loop has changed, right? So this is the loop, while x is greater than 0, do x equal to x plus 1. So again, right, if you think about this intuitively, right, you are starting in a state where x is greater than 0, and this loop, right, it just keeps on incrementing the value of x. So intuitively this loop will never terminate, right? So there will be non-termination, right? And since this loop doesn't terminate, there will be no states, right, which will exit out of this loop. So in the strongest post condition, you are always looking for states where the entire program is executed, right? So here, which means that the entire program has finished its execution, but here there will be no state obtained after finishing the execution, right, because no execution will actually terminate. So there will be non-terminating execution, so therefore this will be actually false. Okay. So the strongest post condition for this will be false. And again, right, you can use the procedure, right, but when you use the procedure, you will see that the procedure itself will run into an infinite loop, right, because you will keep on discovering new values, right, of these fi's. So you may never be able to stop. So the stopping criteria, right, which is there, which is that this one of these fk's, right, should imply the earlier fi's, that will never happen because you will keep on discovering new states. Okay. Okay, so now we have covered the strongest post condition operator for all the different kinds of program statements, right, in the IMP programming language. So you covered all the base statements, we covered all the compound statements. So in general, right, now we know, right, how to compute the strongest post condition of f for any program C, right. So this program C can be any program in the IMP programming language, and I know how to compute, right, at least theoretically, right, how to compute this SPFC. But now I want to use SPFC for encoding the verification problem, right, which is, so we have seen two versions of the verification problem, right. One is the error based version, right, where no error state is reachable, right? And the other is the Hoare logic, right, the Hoare triple based version, right, where I have this precondition, postcondition triple. So both those versions we will now reduce to this SPFC. So first is the error conditional, right. So given a program C with assertions, I say that the program C is safe, right, which means that the program C has no error violation, it has no assertion violation, if this particular formula is valid, right? So this is a formula here, right? So what is this formula saying? It's saying that the strongest post condition of a state error equal to 0, right, and the program C, this should imply error equal to 0, right? So this is, so I know how to calculate SP of error equal to 0 comma C, right? So because I know how to do this for any program C, so I calculate this formula and then I construct this bigger formula, right, which is SP error equal to 0 implies error equal to 0. So if this bigger formula is valid, then the program is safe, right? And again, intuitively, this is because if this formula is valid, that means that all states, right, which are reachable after executing C on any state where the value of error is equal to 0, all those states will also have the value of error equal to 0, right, which means that the value of error never becomes non-zero, right? So the value of error always remains 0. This means that no assertion is violated, because once an assertion is violated, right, recall that this strongest post condition, right, of F, this assert G, if the assertion is violated, then this strongest post condition becomes true, right? And once it becomes true, right, that true will just filter through all the way to the end of the program, right? And you will get, so you will not be able to show, right, that this error is equal to 0 at the end of the program. On the other hand, if an assertion is never violated, right, which means that the value of error will always remain 0, right, and therefore you will be able to show that this formula will be valid, right, which is that SP of error equal to 0 comma C will imply that error is equal to 0. Okay. So in order to prove, right, again that a program is correct, all you need to do is you need to apply the SP procedure. So the SP procedure is a syntactic procedure, right, because given the kind of program C, right, I can use the various formulations, right. So if C is a sequential composition, I use the formulation for sequential composition. If it's a while loop, I use the formulation for while loop. If it's an if then else, I use the formulation for if then else. And in this way, similarly for each base statement, right, I know exactly what will be the formulation. Okay. So I can use that formulation to syntactically calculate this formula, right, and then once I calculate this formula, I can just give it to an SMT solver, right, and if the SMT solver says that this formula is valid, then my program is safe. So this is the ideal scenario, right, where we are essentially constructing a formula, right, and then giving that formula to the SMT solver in order to determine whether the program is correct or not. Of course, I mean, can we always calculate this SP, right? So we have already seen, right, that for while loops, for example, right, you may not be able to calculate this SP at all, because you may have to calculate an infinite number of values, right, of those Fi's for an infinite number of iterations, right. So we don't have a procedure which is guaranteed to terminate, right, but if it does terminate, then we will definitely get this formula, right, and this formula, if it is valid, then the program will definitely be safe. Okay. Now the second is the Hoare triple based formulation, right. So given this Hoare triple PCQ, I say that this Hoare triple is valid, right. So this is saying that the program is safe, right, if this particular formula is valid. So again, we are constructing a formula. This formula is SP of P comma C implies Q, right. So again, SP of P comma C, this encodes all those states obtained after executing C, right, after finishing the execution of C, right, on a state which begins in P, right. So if this entire set of states is contained inside Q, right, which means if it implies Q, then obviously the Hoare triple will be valid. Right. So the definition of this Hoare triple, right, was that if you start the program C in a state which satisfies P, after finishing the execution of C, you should always be in a state which satisfies Q, right. And in fact, if I start the program in a state which satisfies P, then I will end the program in a state which definitely satisfies this SP P comma C, and if this SP P comma C also implies Q, then I am in a program state which also satisfies Q, right, and therefore the program is safe, right. So if this formula is valid, then the Hoare triple is also valid, which means that the program is safe. Okay. So for both of those the two kinds of specifications, right, that we have seen, we can use the strongest post condition procedure in order to reduce it to the satisfiability or the validity problem in this case, right, of first order logic. This is of course provided we can calculate the strongest post condition, right. So if you can calculate the strongest post condition, then you can do this particular reduction. Okay. So we don't have a decidable procedure, right? So the issue is that in order to calculate this SP, right? So if my program doesn't contain loops, then yes, I have a procedure, but if it does contain loops, then because of the infinite computation, right, that's required, or potentially infinite computation that's required to calculate the strongest post condition, we don't have a decidable procedure. So due to the unbounded computation that's required for while loops. So let's try to think about an example, right, of f and c such that SP f comma c requires unbounded computation, right. So in fact, if you try to calculate this SP f comma c, then you will never be able to terminate, okay. And of course, such an example has to involve a while loop, right, because for every other kind of program statement we already have a computation which will terminate, right. So but for while loops it may not terminate. Let's think about an example where it doesn't terminate, right. So as a sort of an illustration, right, of the entire SP procedure, let's look at this program, okay. So this is a program that we have seen way back, right, when we started the module, right? A simple program which counts up to n, okay. So it has this assumption, right. So it starts with this assumption that I is equal to 0 and n is greater than or equal to 0, right. And then it just counts up to n, right. So while I is less than n, I equal to I plus 1, and finally, right, we know that this program is correct, right, in the sense that when we reach line number 4, we are guaranteed that the value of I will be equal to n, okay. So this is a safe program. Let's try to reason about its safety, but using the strongest post condition procedure, right. So this is a program with assertions, right. So therefore we will use the error state based formulation, right. So the error state based formulation was that if you calculate the strongest post condition of error equal to 0, comma c, this should imply that error is equal to 0. This formula should be valid, okay. So we want to calculate this, right, which is SP of error equal to 0, comma c. So SP of error equal to 0, c is this entire program, okay. So here we are using, this program is using sequential composition, right, because there are 3 statements, right. So for sequential composition, we know that we can simply calculate the strongest post condition of statement one after the other, right. So this SP of error equal to 0 and the entire program C, right, which in this case consists of these 4 lines, right. So I have this 1, 2, 3 and then 4, right. So we know that this is simply SP of error equal to 0, 1, which is the state obtained after executing just the statement 1. So this I am indicating by this 1 colon, right. So 1 colon means that I have executed the statement 1, and then this has to be supplied as input, right, to the statement 2, and this in turn has to be supplied as input to the statement 3 and so on, okay. So this is actually equivalent to this, right. So I am going to calculate, I am going to propagate this state error equal to 0 through all the program statements one after the other, okay. So let's first propagate it through the first program statement, right, which is this assume statement. So SP of error equal to 0 and the first program statement, which is the assume statement. So again we will simply refer to what we have calculated earlier, right. So what was the SP definition for an assume statement, right. So for an assume statement it was just f and g, right. So this is f, the assume statement is g, so this is f, this is g, so I get f and g, right, which is error is equal to 0 and I is equal to 0 and n is greater than or equal to 0, okay. So this in turn, right, this will be supplied as input to the SP computation for the second statement, right, which is what I am doing here, right. So of course this second statement is a while loop, right, and for while loop I already know, right, that if I want to compute the strongest post condition for a while loop, I need to compute all of those fi's, right. So I need to compute f0, f1, f2 and so on, right. So f0 in particular, right, is simply going to be f itself, right, which is this error equal to 0 and I is equal to 0 and n is greater than or equal to 0. So what I am trying to compute here is f1, right. So f1 was given by strongest post condition of f0 and g comma c, right. So this is the states obtained after executing one iteration of the loop, where this c is the body of the loop, right, which is here. So SP of f0 and g. F0 is this, right? So this is F0. G is I is less than n, so this is G, and C is my body of the loop, right, which is statement number 3, right? So I equal to I plus 1. So this is the computation of F1, right? This whole thing is the computation of F1. Okay. Now again here the statement number 3, right, this is an assignment statement, so I use the formulation for assignment statements. So this is the formulation for assignment statement, right, that there exists V, right, such that F, right, which is this formula, so error equal to 0 and I equal to 0 and n is greater than equal to 0 and I is less than n, and the FOL encoding, right, of the assignment statement, right, which is I prime equal to I plus 1 and frame I, right. So this is nothing but row of I colon equal to I plus 1. This is the FOL encoding, right, of the assignment statement, which is I prime is equal to I plus 1 and frame I, right. So frame I just says that every other variable retains its value, right. So for every other variable except I, its primed version is equal to its unprimed version. Okay. So now for this particular formula, right, I need to again, right, do quantifier elimination. So I need to eliminate all of the existentially quantified variables. So this is I, n and error, and I need to ensure that only the primed variables survive, right. So again, if you look at this formula carefully, right, so I have I prime is equal to I plus 1, right, and I also have I equal to 0. So what can I say about I prime? So I prime is definitely going to be 1, right. What about the rest of the variables? So error prime is going to be 0, right. So I have I prime, I have error prime. Now only variable remaining is n. So what can I say about n? So n prime is again going to be just equal to n, right. But I also know something more, right. So I know that the value of n, right, is greater than I, and I know that I is equal to 0. So the value of n, so from both these statements, right, you can surmise that the value of n must be greater than 0, and I know that n prime is also equal to n. So therefore the value of n prime must also be greater than 0. So I get I prime is equal to 1 and error prime is equal to 0 and n prime is greater than 0. So this is equivalent to formula, this formula. So this is obtained after eliminating all the existentially quantified variables. So here I have a formula only containing the primed versions. So once I have a formula which only contains the primed versions, I simply substitute, right, it with I substitute every primed variable with the unprimed variable, right. So I get I equal to 1, error equal to 0, and n is greater than 0. So that's what I get. So error equal to 0, I equal to 1, and n is greater than 0, which I have written as n is greater than or equal to 1, right. So assuming that we are in the theory of integers, right. So assuming all these variables are integers, n is greater than 1, greater than 0 is equivalent to n is greater than or equal to 1. Okay. So this is the formula that I get. So this is F1, right. Now again I need to calculate F2, right. So F2 again is the strongest post condition of F1 and G comma C, right, where C is this statement 3, right. So I should say the statement 3 here, and again, right, so you can try to do this calculation, right, and what you will end up with is this particular state, right? So this is F1, this is F2 rather, right? So this part, right, this is F1, so F1 and G comma C, right, which is the statement 3. So if you do this calculation, right, so you will end up with this state which is error equal to 0 and I is equal to 2 and n is greater than or equal to 2, right. And again, right, so once you calculate F2, you should ask, right, whether F2 implies F0 and F1, right. And in fact F2 doesn't imply F0 and F1, right, because in F0, right, you had I equal to 0, right. So remember, this is the input state, right, from which you are starting the while loop. In F1 I had I equal to 1, but in F2 I have I is equal to 2, right. So in fact every time that you execute one iteration of this loop, you are going to see a new value of the variable I, right. So therefore none of the so this is not going to match the value of I that was seen during any of the previous iterations, right. So therefore you will always discover a new state in every iteration of this loop. Okay. So therefore this computation is actually never going to end, right. So this is an example of an unbounded computation, right, because every time you need to keep on calculating new values of fk, right. So fk is for new values of k rather. For every iteration you need to calculate a separate fk. So in the end, right, you will get this infinite, a formula of infinite size, right. So you will have I equal to 1 and n is greater than or equal to 1, right. So this whole thing, right, by the way, so this is f0, right. So error equal to 0 is common among all, right. So I just factored out this error is equal to 0, right. So if you look at f1, right, so f1 had error equal to 0, f2 had error equal to 0 and so on, right. In fact error value is never affected, right, because this loop doesn't contain an assertion. So the value of error will continue to remain 0. So I just factored all those values out and the rest of the formula, right. So this is f0 or f1 or f2 dot dot dot, right. So I is equal to 0 and n is greater than or equal to 0, or I is equal to 1 and n is greater than or equal to 1, or I is equal to 2 and n is greater than or equal to 2 and so on. Okay. And finally I have this not g, right. So this is the strongest post condition for the entire while loop, right. So the strongest post condition for the entire while loop, right, was this OR of f i's I equal to 0 to infinity and not g. These are all the states which will exit out of the while loop, right. So where the values of I will be, where the loop condition will not be satisfied, right. So I will be greater than or equal to n. Okay. And again, right, if you manually, right, kind of squint at this formula, right, so you will see that there is a pattern here, right. So among all of these infinite disjunctions, right, there is a pattern, right, which is that I is equal to 0 and n is greater than or equal to 0. From this I can see that the value of n is actually greater than or equal to I. Similarly, this is true for every other state as well, right. So I is equal to 1 and n is greater than or equal to 1, I is equal to 2 and n is greater than or equal to 2 and so on, right. So in each of these formulas, right, the value of n is actually greater than or equal to I. So in fact this cannot be done manually, rather this cannot be done automatically, but manually, right, you can kind of see that this entire giant infinite formula is actually equivalent to n is greater than or equal to I. So instead of this entire infinite formula, I can just replace it with n is greater than or equal to I. Okay. So once you get that, you will have n is greater than or equal to I and I is greater than or equal to n, which means that I is equal to n. Right? So that's what you will get. And now once you have this state, so now I will, so this is the strongest post condition of the while loop, that in turn will be fed to the strongest post condition for the assertion, right. So you will calculate the strongest post condition with this particular state, right, error equal to 0 and I equal to n with this assertion, right, assert I equal to n. So the strongest post condition of error equal to 0 and I equal to n, which is supplied as input, right, to the statement number 4, right, which is this assert I equal to n. So again this we are just using the formulation, right, that we saw for assert statement. So which is there exists V, right, this is F and not G, right, or F. So this is just F, this is the input, right, so this is F. Okay. So here, right, this particular formula, there exists V, error is equal to 0 and I is equal to n and I is not equal to n. V is just error F and V, I and n, right. This particular formula is false, right, because you are saying I is equal to n and I is also not equal to n, right, which is essentially saying P and not P. So this particular formula is false and therefore false or F just gives you F, right, which is error is equal to 0 and I is equal to n. Okay. And this is the strongest post condition for the entire program, right, and you can see that this particular formula, right, actually implies error is equal to 0. So this formula is valid, right, error is equal to 0 and I is equal to n implies error is equal to 0, this formula is valid. So because this formula is valid, therefore this program is safe, right, and therefore you will never get an assertion violation. Okay. So this is the end-to-end computation, right, of the SP procedure and also how to use the SP procedure for verification, right. Of course, this example also demonstrates, right, that the SP procedure may not terminate.